Okay, good.
Спасибо.
So when you think of a vector field, you should imagine something like this. Say, think of wind velocity on the Earth's surface. So at every point on Earth, on the Earth's surface, you have direction and well, velocity of wind. So you have kind of a vector which is tangent to the Earth's surface, and you can consider how particles move with the wind. And this is the notion of integral curves of a vector field that we are going to discuss. So, I want to define the notion of vector fields intrinsically. So I give myself a smooth manifold M. And a vector field is, so we already defined for every point, say A in M, we already defined the notion of tangent space. This is tangent space. At A. And informally, a vector field is a function that assigns to every point in M a tangent vector at this point, right? So you have a manifold, and at every point on this manifold, you have a tangent vector. So this notion itself, as I stated, it is not very useful. I want to consider, I want to make sense of, I want to consider such functions, such tangent vectors, which vary smoothly when A varies, right? And so to make sense of this, I will first define what's called the tangent bundle. So tangent bundle is going to be, well, so tangent bundle right? So it's, first I define it for you as a set. So Tm is, as a set, is just disjoint union over all points A in M of TAM. Okay. So, well, another way of putting it is, I look at the collection of all pairs where A is a point of M and theta A is a tangent vector. So here A is in M and theta A is in the corresponding tangent space.
So now theta is not the vector. Now it's a whole tangent space.
No. Theta A is a vector in the tangent space. So okay. I look at the collection and the set of all pairs. So pairs A, comma, theta A, where A is an arbitrary point of M, and theta A is a vector in the corresponding tangent space. So, okay, so this is clearly there is a bijection between this set and this set, tautological. I take disjoint union. So a vector in one copy of this tangent space, remember Z. Is it okay?
Yes.
Okay, so someone, okay. So now, clearly, so this is a set, but it's equipped with some additional structure. Namely, well, first of all, I have a map from this set to M, which just takes a pair A, comma, theta A, and sends it to A, right? So it's a set which is equipped with a map to M, and I will call this map P. So this map has a special property that the fibers of this map, so pre-image of every point in A in M, is a vector space. Namely, this is a tangent space, T sub A M, by the very definition. So I want to put more structure on T M. I want to put a structure of a smooth manifold on T M. And in order to do this, so let's choose a local chart. On M. So say it's an open subset of M and a diffeomorphism between U and say Rn. Okay, so let me give a name to this. This will be phi sub U. Okay, then so this is local chart. Then, as we proved last time, this kind of local coordinates specify bases in each tangent space at points of U. Namely, so for every point A in U, we have vector fields, we have vectors d over dxi so these are, we think of this as elements in the corresponding tangent space, and they form a basis. Okay, so one way of thinking, well, one way of thinking of the tangent space is we can think of these elements here as derivations, right? Maps from functions defined in a neighborhood of point A to real numbers that satisfies the Leibniz formula. And so this map phi identifies functions on U, smooth functions on U, with smooth functions on Rn. And on Rn, I have partial derivatives. So I can take partial derivative evaluated at point phi of A and get a map from functions on Rn to real numbers. So this defines a derivation from functions on U identified as functions on Rn, right, to real numbers. And these are my vectors. So this is, I have a canonical, well, a chart defines a basis. This is this one. So therefore, if I I can use this basis to identify, to construct a map, which I will call psi u from u times Rn to this set Tm, right? So set of all pairs consisting of points of M and tangent vector at this point. So namely, so what we can do, we can simply send point A, and here I have coordinates y1, yn, to the following point in Tm. So again, a point of Tm is, I think of this as a pair consisting of a point of M, which is going to be my A. And so I also have to specify a tangent vector at this point. But now I have a basis, right? So I can simply write every tangent vector is a combination of these vectors. And I will use these numbers as this yi. I think of this as coordinates on this tangent space. So I will simply write d over dxi sub a, right? So this is now an element of TAM. And of course, every element in TAM can be uniquely written in this form because this is a basis. So in fact, what we have is a bijection between P inverse of U, right? Remember my notation. So P denotes this projection from set Tm to M. So because every tangent vector at A can be written in this form, this is clearly a bijection. So now I want to define a smooth structure on Tm by declaring that these maps are coordinate charts. So of course, one has to verify that this is indeed a smooth atlas. So what one really has to do, one has to check that if we choose another coordinate chart, so say, so suppose I have another, if maybe U bar, it's another open subset, and phi U bar is another chart. Then I have to show that the transition maps, right, are smooth. So let's see what it means. Okay. So you have we have M, we have U bar, and we have this map phi U bar diffeomorphisms, and then we can look at the intersection. This is an open subset of M, and on this intersection, at every point of this intersection, we have two bases in the tangent space at point A. So let's see how these two bases are related. Well, they are related by the chain rule. So if you can express one basis is dxi, d over dxi, and another basis is d over, well, I will call it dxi bar. Okay, so this is j. So let's see how these two bases are related. So the formula is the following. It's sum over oj dx bar j over d xi. Okay, so it is understood here that well, xi and xj bar are local coordinates here, right? So you can express, you can think of these functions xj bar as functions in xi. So you can take partial derivatives. So, and you evaluate these partial derivatives at A. This is the expression. And again, this is just the multivariable chain rule. Using this formula, we can express, so we have this map, and we also have the corresponding psi bar map defined on the intersection of u and u bar. And we can compute the composition. So psi inverse u bar psi u. So this is going to be a map from so we first take well, I will write down a formula for you. So it's it takes point with coordinate x1, xn, y1, yn, so it's a map from, let's see, I'll write it here. So we think of this as a map from u intersected u bar times Rn to itself, right? And here is the formula for this map. It's simply x1 bar, xn bar, and here I will have sum over dx1 bar over dxi, and here I have I. This is sum over all I, and then it will be sum dx 2 bar dx I yi. Okay. So you see that clearly, well, by very definition, sort of this map is must be identity on the first factor, and on the second factor here, it's a linear map. So if you fix a point in the intersection of u and u bar, it's a linear map, and the coefficient, the entries of the corresponding matrix are these partial derivatives. And by the very definition of a smooth chart, these partial derivatives are smooth functions. Okay, so this map is smooth. And therefore, it defines a smooth atlas. So it proves that if we consider all open subsets, all smooth charts, so if this is a smooth atlas on M, then this psi I will say that this is simply P inverse of U alpha, and the map should be psi alpha inverse, right? Inverse is put here because, because I want a map from an open subset of the tangent of Tm. These maps define is smooth atlas. Smooth atlas for Tm. So we get a smooth structure on Tm, which depends only on the smooth structure. So definition, Tm with the above smooth structure is called a vector tangent bundle. Tangent bundle. Okay. So so we have a smooth manifold Tm, and we have a map, I called it P, from Tm to M. We just forget the tangent factor. So it can be shown, and it's almost immediate, that P is smooth, right? Simply, it follows immediately from definition of, construction of coordinate charts on T. So now I can define finally the notion of a vector field. A vector field on M is a smooth map from M to T such that its composition, let's call it theta, such that composition of P and theta is the identity, right? So so here is the picture again. So so I have this tangent bundle, and a vector field is what's called a section, right? It's a map in this direction. This is P, and this is theta. So theta assigns to every point of M a vector in the corresponding tangent space. But now, because Tm is equipped with a smooth structure, it makes sense to say that theta is smooth, right? So, in local coordinates, so a vector field, say, local coordinates identify an open piece of M with Rn, and so it gives it basis in every tangent space. So then a vector field can be uniquely written as a combination of basis vectors dxi at x with some coefficients. And these coefficients are smooth functions. So maybe just smooth functions, right? So, so given a vector, for example, a vector field on Rn is the same as given a collection of n smooth functions. So let me give you before I proceed with giving you some kind of more geometric interpretation of vector fields, let me spell out some extra structure Tm has. So let's say that Tm is a special case of a very important notion in mathematics, in differential geometry, topology, algebraic geometry, namely a vector bundle. So a real vector bundle over M is a smooth manifold. Is a manifold manifold E with together with a map P from E to M and another piece of structure and vector space structure on the fibers of this map. Fibers, by definition, are preimages of points. So for every point x in M, I can look at the preimage of this point. This is a subset of E, and a vector bundle consists of, well, it's a smooth manifold E together with the structure of a vector space on this set, right? This is a piece of data. such that certain conditions are satisfied. So what are these conditions? The conditions are the following. So for every point A in M, there exists an open neighborhood and a diffeomorphism. Between the preimage of this open neighborhood and U times Rn. Okay, maybe I will say a vector bundle of rank M and Rn. So this diffeomorphism must have extra properties. First of all, it must commute with projection to U. So here I have map P, and here I have also projection to U. And let's give a name to this. Let's call it psi U. So first condition is that if I take psi U, compose it with this projection, then it must be P. So meaning that this diagram is commutative. So this is the first condition. And the second condition, well, look, so so that means that once I have this property, it means that this map psi carries a fiber of this map over any point for any x in U, if I consider P inverse of this point and simply well, x times Rn. So I can by this property psi defines a diffeomorphism between these two, well, at least a bijection between these two sets, right? But now a structure of a vector bundle consists of vector space structure on every fiber. So this is a vector space, and this is also a vector space because Rn is a vector space. And I require this psi to be linear. Okay. So a linear map from m-dimensional vector space to itself. So this is a vector bundle. You can think of this of a vector bundle. Well, you see as a this E as a set. It's disjoint union over all A in M of vector spaces. So P inverse of A. And this is a vector space. So it's kind of a family of vector spaces parameterized by points of M together with a smooth structure on this disjoint union. That's what it means to have a vector bundle, right? And this smooth structure must have some kind of extra property. It must be compatible with the vector space structure, right? So it's locally should be kind of isomorphic to U times Rn. This map psi U are called trivialization of a vector bundle. Good. So again, when you think of a vector bundle, tangent bundle is a very good example. And we also have a notion of a section. A section smooth section is of a vector bundle is a smooth map from let's call it theta from M to E with such that the composition of theta and P is identity, right? So, the set of all smooth sections has an extra structure. Well, so because fibers of E, so what is a smooth structure? So for a smooth section, what is this section? For every point of A, we have a vector. Theta specifies a vector in this vector space. So therefore, we can add sections, right? And we can also multiply a section by a number, not even by a number. We can, for every point A, we can multiply the corresponding vector by its own number. So smooth sections form a module in the algebraic sense over the algebra of smooth functions on it, right? So namely, if I have theta and the function, I can simply define the product at point A as theta of A. Theta of A is an element of the fiber of E over point A multiplied by the number. So this is an element in pre-image of A. Again, this is called the fiber of a vector bundle, and this is the usual notation for this. It's E sub A. Okay. So it's easy to verify that if F is a smooth function and theta is smooth section, then this new section is again smooth. Why it's how to verify this? Well, it's a local statement, so it's enough to verify this property for the trivial vector bundle, which is just U times Rm that maps to U by the projection. And then a section, right? A section of this trivial vector bundle is the same as a smooth map from U to Rm. And of course, every smooth, this structure of a module amounts, so if you have a smooth function from U to Rm, you can multiply it by any real valued function on U. And you get again a smooth map from U to Rn. So this amounts just to the fact that product of two smooth functions is again a smooth function. So there is an adjective real in this definition. So you, in principle, you can replace this real vector space structure by a complex vector space structure. So let me write here R. Yes, it's a vector space over R, but replacing R by C, you get a notion of a complex vector bundle, which is also useful. So consider. So I made this definition to kind of put this construction of a vector field into some more general framework. So kind of the key example of a vector bundle you should have in mind is the tangent bundle. You can also take, if you have a vector bundle, you can apply any linear algebra construction you have for vector spaces. Like you can take the dual vector bundle. The dual vector bundle is obtained by replacing every fiber of this P, which is a vector space, by the dual vector space, right? That's how you get the notion of the cotangent bundle. Or you can take, say, direct sum of two vector bundles, right? You do it just term-wise, fiber-wise. Okay, so how you can construct vector bundles? Well, how to think of this? So let me give you some examples of vector bundles. So what is a vector bundle? So we have M, and so locally, a vector bundle is nothing else but the product of an open piece of M and Rn, right? So imagine that you have, it's a locally trivial vector bundle. Imagine that your M is covered by two open sets, U1 and U2. Then, and suppose that my vector bundle is trivial over U1 and U2, meaning that I have this trivializations psi U1, which is a diffeomorphism, fiber-wise linear diffeomorphisms between this and U1 times Rn. And I also have psi 2, which is this U2 times Rn. So that means that on the intersection, I have two different, you can look at PU1 intersected U2, and I have two identification of this with, this is identity. So this is my psi U1, and this is psi U2. Two different identifications of this with, sorry, U1 intersected U2 times and here it's U1 intersected to U2 as R. So this is a diffeomorphism. It's simply a composition of psi U1 inverse and psi U2. But this diffeomorphism is not an arbitrary, right? We have some extra property of psi, compatibility with a linear structure. So what are these properties? So first of all, it must take a fiber over every point, right? So this is a manifold that admits a projection to U1 to times intersected with U2. So the first coordinate, on the first coordinate, this map should be the identity on the first factor. And moreover, if I fix a point in this intersection, then the corresponding map from Rm to Rm must be linear. So you can think of this map, which is again psi U1 inverse composed with psi U2. This composition you can think of this as an element in, okay, I will better write it. So, so this is a map from U1 intersected U2 to the group GL MR, right? So again, so for every point in this intersection, so if you fix a point A here, so this map restricts to a linear map from Rm to Rm. Moreover, it must be bijective map, so it must be a linear and invertible M times M matrix. So that's how this map defines a map from this smooth manifold U1 intersected U2 to the group GLMR. So this group GLMR is an open, well, as a set, it's an open subset of the group of all M times M matrices, right? Which is just R M squared. So this is an open subset here, and as well, it's an open subset of Euclidean space, so it acquires as an open subset of Euclidean space. It has a smooth structure. It has actually a global chart. It has this embedding defines a diffeomorphism, well, teleologically of this set and open subset of the Euclidean space, right? The condition that the determinant of a matrix is not equal to 0 is the matrix is invertible is an open condition. So this is not just a group; it's also a manifold. It's smooth manifold, and in fact, it's what's called a Lie group. So it's a group with a smooth structure such that the product, which is a map from GLM to times itself to GLM, is a smooth map, as well as the inverse map that takes a matrix to its inverse. So these maps must be smooth. So saying that this is a diffeomorphism, a linear fiber-wise linear diffeomorphism, is equivalent to saying that this map to GLMR is smooth. Again, so GLMR is equipped with this smooth structure coming from this embedding. And this is just saying that you have a matrix with coefficients in smooth functions on U1 intersected U2.
Excuse me.
Mm-hmm.
So on the right hand side, down on the slide, we can see that so we have U1, U2 intersected times Rm, then the function, the composition of psi, the different ones, and the same spaces U1 intersect U2 and Rm. And so do I understand correctly that this diagram shows that we take some element of intersection times Rm. So this point looks like A and M numbers.
Yes.
Then this composition of psi takes this point, so A plus M coordinates, and it leaves the point A the same, and it somehow changes the M numbers, which we just
exactly.
Okay.
So you have this map takes A comma V to a point of the form A comma let me call it GA of V, where GA is an element of GLM.
So because on the left hand side, it looks like as if the composition of psi takes just point A, and then makes an operator out of it. But on the right hand side, we see that it takes a point and the vector and makes a point and another vector, and it's not really clear how is it the same as just take a point and make an operator out of it. So
sorry, I'm not sure that. So let me. So you see, so so you have this map here, this composition, and so if I understand your question correctly, you're asking how this this map at the right hand side of this diagram gives me a map from U1 intersected U2 to GL.
Well,
okay.
I believe that we just do I answer correctly that we just takes the vector V and then okay, I don't quite understand.
Yeah, so you take A and send it to GA, which sits here. So let's consider a subset here, which is A, comma times Rn. So this is a subset here, and so my composition maps this subset to itself, right? And the requirement is that this map is linear, meaning that so if I identify this subset with Rm, it becomes a linear map from Rm to itself. So that means that it gives rise to a matrix, which I call here G sub A. It's an M times M matrix. So for every point A, I get a matrix. This is my G sub A. I get a matrix. And so the map here takes A to this matrix.
Okay.
Okay. So to summarize, so if I have a vector bundle, say on the union of U2 and U1 and U2, together with these trivializations, psi U1 and psi U2, then well, the kind of collection of such datum is well, it is in one-to-one correspondence with smooth maps from U1 intersected U2 to this group GLM. So what I'm saying is that you can recover, if you know these maps, you can recover the vector bundle on U1 union U2. So I think it will be better if I can definitely write it here. So so you can recover your vector bundle, which is this over U1 union U2, as the quotient of U1 times Rm, U2 times Rm, I take disjoint union of these sets and I mod it out by some equivalence relation. So here, vectors A, comma V, this is a point here, is said to be equivalent to point B, comma W if A is equal to B, if A and B are the same points, therefore they are kind of points of the intersection, right? Moreover, vector V is equal to, well, this map, which is psi U1 inverse psi U2. I think of this as element of GLM. Well, I evaluated at A, right? So this is now an element of GLM. And I can apply this element to W, right? So, so here is a picture. So I have two open sets. My vector bundles over these two open sets are trivial. And now here I have intersections. So this is U1 intersected U2. This is U2. So here I have also U1 intersected U2. And now, so I can glue U1 and U2 along this intersection. I made them disjoint, but now I can glue them together. But, and so in fact, using this psi, this elements in GLMR, I can also glue the fibers, actually the vector bundle itself, right? So not only I have to glue U1 and U2, I have to glue a fiber over a point A with the fiber here over the same point, right? So I have to identify these two fibers in order to do the gluing. So, and I use these matrices to do the identification. So this must be a linear identification to give it a structure of a vector bundle. So kind of the moral of this is that you can construct vector bundles on a manifold by gluing just Cartesian products of open pieces times Rm using this transition maps, transition functions, which are maps from open pieces to the general linear group. So I will give an example of what you can do. So take simplest example. Take M be let n be S1. So I'm going to cover. So this is circle, and I'm going to cover it by two open pieces. So let me here. So let's see. Yeah. So So this is going to be my U1, and U2 is going to be probably I can still use some. Let me see if I can change color. Okay, we do select. Not very. Oh, okay. Maybe I can do this. No, doesn't work. Why doesn't work? Okay. Now it works. So this is my U2. Okay. So you see that I have I choose a cover of the circle by two open sets, each of which is isomorphic to open interval. So in order to specify a vector bundle, so I can take U1 times R and take union of U2 times R. And all I have to do is to specify a map so in order to define this equivalence relation, this equivalence relation is a map from U1 intersected U2 to the general linear group. Well, here it's my rank of a vector bundle I want to construct is 1. So this is just R star, right? So any smooth map from the intersection of U1 and U2 gives rise to a vector bundle of rank 1 on this circle. So let's make a choice. So this U1 intersected U2 looks like disjoint union of two intervals, open intervals. So, and let's define this map to be 1 here and -1 here, okay? So, so I take this very simple smooth manifolds. Well, they are actually diffeomorphic to R2, and I glue them together using this map, right? So let's try to draw a picture. What will actually happen? So, in order to draw the picture, I'm going to identify R with an open interval. I cannot write infinite interval. So let's. I cannot draw infinite interval. So let's make something my life a little bit simpler by. Okay, I will try to draw this. Okay. So what I claim that what you'll get is what's called the members band if you do the gluing, right? So let's, yeah, I think it's more or less correct. Maybe I should erase part of this picture. Oh, sorry. Okay, so you kind of take a strip, you glue this interval with this one by first twisting it upside down. So you identify this point, this end with this one. So that's how you do the gluing. And so what you get is Möbius strip.
Excuse me.
So, this Möbius strip, well, I think of this, it has a map to S1, right? So this kind of, you can you can take a point on this member strip and project it to the to this line here, right? To this interval, which gets glued to S1. So the member strip can be projected to S1, and the fibers of this map are open intervals, which are, of course, diffeomorphic to R. That's how the total space of this vector bundle, this is my E, looks like. This is the projection to S1. This is P.
Excuse me.
Yes.
What would happen if we had 1 and -2, for example?
It will be the same vector bundle.
So only the sign is important, yes?
Yes. In fact,
okay.
One can show that there are precisely two vector bundles of rank 1 on S1. One is a trivial vector bundle, M times R, and another one is this. And you're absolutely right, only the sign is important. So, very good. So how to see that this vector bundle is not trivial? Maybe, so why,
what is a trivial one?
Yeah, so why E is not trivial? What is a trivial vector bundle? A trivial means that a vector bundle is said to be trivial if there is a diffeomorphism between E and M times R, which is linear on fibers, right? Meaning that it's not an arbitrary diffeomorphism. First of all, it makes this diagram commutative, and secondly, it's linear on fibers. So a vector bundle is trivial if and only if this trivialization exists globally. If I can take for you the entire M, right? This psi u is called local trivialization. And if you have a global trivialization, if you can take for um, the vector bundle is called trivial. So if E again is just M times Rm with the obvious vector space structure on the fibers. How to see that E is not trivial? So if I choose another map for the gluing, for example, if I pick 1 here and 2 here, I claim that the corresponding rank 1 vector bundle would be trivial actually. But this is not. So how to see this? So here is a very useful construction. So take E. So you have a vector bundle. Suppose you have any vector bundle. So this is P. Every vector bundle has a canonical section, which is called the zero section, right? So although there is no way to construct kind of a canonical section of a vector bundle, non-vanishing section, because well, a vector bundle again is a kind of a family of vector spaces, and you don't have a basis in this vector spaces. So you can pick, of course, a vector in every fiber, but it's not obvious that you can make this kind of collection of vectors very smoothly, depends smoothly on points of M. In fact, we are going to see that, say, the tangent bundle on S2 does not have non-vanishing sections, right? That's well, has implications to sort of real life. It asserts that at every time there is a point on the sphere where there is no wind. Wind velocity is 0, right? So, but well, let's postpone it for later. So at least there is one section, 0 section, right, that assigns to every point of M the 0 vector and the corresponding factor. So, and let's take so we can think of M as sitting along in E. So this is the 0 section. So let's take E and remove M. Okay. So so if so let's apply this construction to the example here. So well, what happens? So my E is diffeomorphic to the Möbius strip. And what happens if I remove this circle here, right? So this so I have this 0 section. What will happen if I remove this 0 section?
Another Möbius strip.
Okay, so what you'll get is the cylinder, right?
White cylinder.
What do you get? Do you think you'll get? So if I have so let's look at these 2 pictures. So this is the trivial vector bundle on S1 over S1. So it's a cylinder. So if I remove well, the correct picture would be here infinite cylinder, but it's homeomorphic, of course, to just product of S1 times open interval. And if I remove a section, right, I just get 2 cylinders. So, but I suggest you to make an exercise, just glue a Möbius strip for yourself, right? So take a piece of paper and turn it, this part, upside down, twist it, and then do the gluing, and then cut it along this line. What do you have? What do you get?
A connected bond.
I claim that what you'll get is a cylinder with whose radius, right, is twice as well. Whose radius is twice of sort of the radius, if I may say so, of the Möbius band, right? It will be sort of thinner, but it will be it will have larger radius. Okay, so it's different.
No, it will be twisted 2 times. Is it true?
Yes. Yes.
Oh, okay.
So it's going to be diffeomorphic to open interval times S1. Very good. So if E were trivial, then E minus M would be diffeomorphic to just disjoint union of 2 copies of this. right? Because if you take, so if E is M times R, if you remove M, which sits here as M times 0, you just get M times R plus union M times R minus. This is, well, 2 copies. Very good. So this observation gives a proof that my vector bundle is not trivial. Okay, so good. So now, so let's go back to vector fields. So we defined vector fields as sections of the tangent bundle. What can you do with vector fields? So let me give you another point of view on vector fields. So next, the title of the next section is vector fields and derivations. Okay, so suppose I have a vector field. Then for every point A of n, I have theta, the corresponding well, tangent vector, theta A, which sits the tangent space at A. And I can think of theta A as a derivation. It's a map from, linear map from the vector space of smooth functions to R that satisfies the formula, the Leibniz formula. F times G is equal to theta A F times G of A plus F of A times theta A of G. So now, as A varies, I get, for every point A, I get its my own number. So I can now define a map, which I will also call theta, from C infinity, from the vector space of C infinity functions on M to itself. By sending, so if theta of F, so F is a smooth function, evaluated at some point A, right, is just theta A of F. Well, so I haven't yet explained why I get a smooth function, but at least I get a function, right? For every, I can apply this construction to every point A of M, and so for every A, I get a number. If I fix a function, for every point A, I get a number, so I can think of the result of this as a function on M. So let's check that it's smooth. And this is almost immediate, because in local coordinates, so locally, so if theta is combination of dxi yi of x, then theta of f, well, it's just so f, I think of f as a function in this xi, so this is just going to be yi of x d f dxi. So, and these are smooth. So that means that this is a smooth function. And property of being smooth is local, so it suffices to do it on for local charts. And so we are done. So theta defines such a map, and this formula can be rewritten. So it means that theta of the product is equal to theta of f times g plus f times theta of g. So a map from a ring to itself, a linear map that satisfies this property is also called a derivation, right? So theta is a derivation on C infinity M. So this is an algebraic notion. It makes sense for any ring, even a non-commutative ring. It need not be commutative if you write the Leibniz formula, the product rule in this form, where you see that I do not interchange f and g, right? So I always preserve the same order here. So it's kind of it makes sense. Well, for any ring. Okay. So now here is a proposition. So any derivation let's say d from the algebra of smooth functions to itself has the form theta for some vector field, smooth vector field, right? So again, so just explain that any section of the tangent bundle gives rise to a R linear map from this this algebra to itself that satisfies this formula, and also, well, we call a map that linear map satisfying this formula derivations. And the proposition asserts that any derivation arises from a vector field. In fact, a unique vector field. Okay, so that gives a completely different way of defining the notion of vector field, which avoids smooth structure on TM, discussion of vector bundles. Well, all we've done so far. So it's just a one-line definition. Any linear map that has this property. So let's give a proof. In fact, we hard part of the proof has been already done. So hard part of the job. So well, suppose I have a derivation. Then for every point of M, we can take a composition of the map of D and the evaluation map. So if I have a function, I can evaluate it at point A and get a number. So F goes to F of A. So if I have a map D from this ring to itself that satisfies this property, then for every point of A, I can take this composition, get a map from C infinity M to R, which satisfies this property. Okay? So therefore, this composition D composed with evaluation defines a tangent vector. Which I will call theta A. It's a tangent vector in TAM. So we're almost done. So we have for every A, for every A we have for every A in M we have tangent vector. So this defines theta, and so we get a vector field theta. The only thing that remains to prove is that theta is smooth, right? So we get what we have so far. So this is our tangent bundle. This is P. So far we get a section, just a map, right? Which is just a map of sets, right? And I want to show that this theta is in fact a smooth map from M to T, right? And what I'm going to use is that this D lands in C infinity functions, not just arbitrary functions. If I start with any section, just set theoretical section, and map theta such that composition with P is the identity, I'll get a map from C infinity of M to just functions that satisfy this Leibniz formula, but these functions that I get need not be in general smooth. So why theta is smooth? Oh, so this is a local question. So we can pick local coordinates, local chart. So then write theta as sum, yi of x d over dxi. So I can write any section in this form. The only question is whether these functions yi are smooth. So, but theta, if I have this, so I know that my derivation d arises from theta, which is of this form, for some function yi. So theta, this theta, applied to xi, just do computation, it's going to be x, yi of x. On the other hand, it's equal to z applied to xi. And this, by definition, is a smooth function. Well, it's a smooth function. Okay. I'm using here definitely partition of unity when I sort of extend derivations from global functions, functions defined globally on them, to functions defined locally on them. So we already did it for derivation at a point when we discussed tangent factors, and here I'm doing this again. So I skipped a kind of a step. So any derivation defined globally on them also gives rise to a map d from C infinity u to itself. That also satisfies the Leibniz formula. Okay, so this is constructed using this bound function. Okay, so so since dxi is smooth, it shows that yi is smooth, and therefore theta is smooth. So we have algebraic interpretation of vector fields as derivations of this ring, and this interpretation makes it possible to define an extra structure on the space of all vector fields. So, well, vector fields, our geometric definition was we defined vector fields as sections of certain vector bundles. So by definition, vector fields form a module over C infinity functions on M. You can add vector fields, and you can also multiply a vector field by a function. But there is another operation on vector fields which is fundamentally important in differential geometry, and that's the notion of Lie bracket, structure of a Lie bracket. So in order to define it, I need an algebraic lemma. So let A be any ring and D1, D2 are derivations. Well, so derivations here mean that these are maps that take sum to sum and satisfies Leibniz form. Okay, then what I can do, I can take, so what can I do with linear maps? I can compose them, right? I can take D1 composed with D2. That's also a map from A to A that takes sum to sum. But unfortunately, well, it no longer satisfies the Leibniz formula, right? So for example, if A is just the ring of C infinity functions on R, D1 and D1 is derivative, right? With respect to the coordinate on R. This is, and D2 is the same map, then this is the second derivative. And second derivative does not satisfy the product rule. It's kind of more complicated. But the miracle is that if you take the commutator of these two maps, which is again a map from A to A, right? And I will write it as D1, D2. This is the notation for this. And the claim is that this map is again a derivation. Okay. Derivation, sorry. Okay, so let's prove it, and then we'll make a break. This is an algebraic statement. So let's just write. It's elementary once the proof is very simple. However, it's not easy to guess that a statement like this is true. So okay, so this is product. Well, this is D1 of D2F times G minus plus D1 of F times D of G, D2. So, and this is equal to, again, apply the Leibniz formula. So this is D1, D2, apply it to F, multiplied by G, plus D2 of F times D1 of F of G. Then I'll have plus D1 of F times D2 of G. And then the last term is going to be F multiplied by D1 composed with D2 of G. So, and now I have to write down the same formula for D2 composed with D1 of G. Let's see what we'll have. So we'll have D2 D1 of F multiplied by G, plus we'll have D1 of F D2 of G, plus D2 of F D1 of G. And then we are going to have plus F D2 composed with D1 of G. Okay, and now you take finally D1 composed with D2 minus D2 composed with D1 and apply it to F times G. So you see that terms where you have kind of second derivative, that is, well, that's the appearance of second derivative here is the reason why this composition does not satisfy the Leibniz formula. So the second derivative gets cancelled. So, right, so when you, yes, so for example, well, I claim that what we'll have is d1 d2 minus d2 d1 of f multiplied by g minus f multiplied by d1 d2 minus d2 d1 of g. So what gets cancelled at these terms? This, so you have this term, you have this term, and here you also have this term and this term. So these four terms gets cancelled, and what you have is, what remains here is this, and this is precisely the message. Okay? So this shows that this is indeed a derivation. So, corollary.
Excuse me.
Bracket.
Doesn't this formula implies a plus instead of minus in the middle?
No, I don't think so, because oh yeah, yes, thank you very much. It's thank you. Yeah, of course, you're absolutely right. Thank you. And that's yeah, it should be plus here. That's the definition of derivation, right? So if I had minus here, I would be in trouble. Thank you. So corollary is that this operation defines an operation on vector fields, smooth vector fields. And this operation called the Lie bracket. Lie bracket. Okay, so let's make a 20 minutes break now, and I'll resume at 6:30. So my plan for the rest of this meeting is to give you some examples of to do some computations with Lie bracket, and also discuss the last problem about the tangent, the vector fields on a sphere, the tangent bundle to two-dimensional sphere, which is semi-modulist. So if time permits, we'll also discuss a problem from the last problem session on partition of unity, though I would am kind of more reluctant to do this because it's very standard result that in many textbooks, so it's not very illuminating. Okay, so we will resume at 6:30.
Okay.
Sorry, do we have homework in this class?
Do we have homework? So far, no, we don't have any homework. So we are supposed, that's a good question. So I'm supposed to follow what's written in the syllabus. So let me check what are our grading rule. So I will answer your question. Give me some time, please. Okay, so according to the course book, the grading rules for this course are as written here. So the final grade will be based on the following items: homework, midterm, and final exam. This is how I'm going to be these items. So this is the percentage of the total grade. The homework is it will not be huge, and it will be mostly computational. And I will send the first homework assignment this week by email, and so you can either submit it a LaTeX document, or you can just write it down and say scan it, or make a photo with your phone and send me a JPEG file. So okay, more questions on the organization of this course. So just for those who were late, so next week we meet at the same time, Tuesday, 7:30, and starting with, and then we will meet on Wednesday at the same time. Very good. So let's go back to math. So we defined an operation on vector fields. So let's make a let's look how it works. So let's take for m just r. Then given a vector field is equivalent to given a smooth function. Any vector field has the form f d over dx. And so what is the commutator? Let's compute the commutator of two vector fields. G d over dx. Well, you do it just by definition. You take a function, you apply first, you take this, well, differentiate this function, multiply it by g, then again differentiate, multiply it by f, and then do it vice versa. And what you'll find, I will just give you the answer. So the answer must be again a vector field, right? So, so a straightforward computation shows that this vector field is f g prime minus f prime g times d over dx. Okay, so what is obvious from this formula or from this definition is that so this operation is definitely skew symmetric. If you interchange these two guys, the commutator just changes the sign. So if another example, if m is R2, so I will not write down for you general formula, but let's just just want to observe that commutator of d over dx, d over dy is 0. This is a fundamental relation that two partial derivatives, if you first take a smooth function, differentiate with respect to y and then with respect to x, that you get the same answer as if you first differentiate it with respect to x and then with respect to y. That's fundamental identity for partial derivatives. Okay, so so what is less obvious from this definition is that so we have the space of all vector fields. I will call it C infinity Tm. The space of all vector fields and so we have a bracket, this Lie bracket. It's definitely a bilinear map from this vector space, skew-symmetric bilinear map from this space to itself. And so it has another fundamental property, which is called the Jacobi identity. So the Jacobi identity is the following. So if you take three vector fields, theta 1, theta 2, theta 3, so and take this iterated commutator, then it's equal to theta 1 commutator of theta 1, theta 2. There are many ways to write it. Theta 3, yeah, theta 3, plus commutator of theta 2 and theta 1, theta 3. So how to memorize this very important formula? So think of, it asserts that this commutator operation, say commutator with theta 1, is a derivation with respect to operation on this vector space given by the commutator. Think of this bracket here as kind of product. Then, as you see, commutator with theta 1 behaves like a derivation. So, and well, proof of this identity. Well, so proof is very well. It's actually very simple. So this is verified by direct computation. What you do verify, there is nothing special about vector fields here. So if you have any vector space and any matrices, well, any endomorphism, just linear endomorphisms over a field, say, over real numbers, then this identity just holds for the commutator of linear matrix, for matrix algebra. So commutator of A, B, C is equal to commutator of A and B minus plus commutator of B with A and C. So what I'm saying is that it's enough, well, so this relation for vector fields is a corollary of much more general statement that for any three matrices, you have this identity with commutators. So here A and B, commutator of A and B is defined as AB minus B. So it has nothing to do with theta I being derivations. It's you just plug this definition in this formula, and it works. Okay. So I will not do this computation. It will not be very instructive. The result itself is very, very, very important, but the proof is well, at least could be some. There are some more conceptual explanations why this is true, but I'm not. I don't think that it's appropriate to discuss it now. Okay, so so a vector space together with a bilinear skew-symmetric operation satisfying this Jacobi identity is called in algebra layout, right? So so this makes vector fields enter a Lie algebra. Algebra. So the most important example of a Lie algebra is the algebra of endomorphisms of a vector space. So you take a vector space of all functions on smooth functions on them and look at this matrix algebra. So it's a Lie algebra with respect to commutator of endomorphisms. And by construction, vector fields is a sub-algebra here. So you look at those endomorphisms that satisfy the Leibniz form, and so this subspace is closed under the commutator. That was the content of the lemma that we have just proved. Okay. So
excuse me.
Yeah.
So on the right-hand side we have C infinity on M. So, and what are the endomorphisms of this space? So how do they look like? It's like the derivations and stuff like this.
No, so we look at all endomorphisms. So inside, so this is an enormous space. So you can, for example, you can, if you have a function, you can consider, every function defines an endomorphism of this space, which is just multiplication by this function. We also have derivations. We also have composition, iterated derivation. So if you have two derivations, you can take its composition. So that's what's called a higher order, second order differential operators. But you have much more operations. So all this so derivations, multiplication by a function, or even higher order differential operators, they depend only on, so if you want to compute d of f at some point x, then the answer, which is a number, depends only on behavior of f and the neighborhood of this point. Or in fact, all you need to know is kind of few first partial derivatives of f at this point. But there are much more operations which are sort of endomorphic, which are global, right? For example, if you if m is like real numbers, you can consider an endomorphism which takes a function f of x to function f of x plus 1, right?
Oh, okay.
That's an example of an endomorphism. So
okay.
this is an enormous space, and I don't have any kind of, there is no way to describe it. But inside you have much more traceable subspace, which is this derivations, right? So okay, maybe since this question has arisen, let's discuss. So we have this. These are vector fields. As I mentioned, another important example of endomorphisms are another class of examples is multiplication by functions, right? So if you have a function, you can, if you have an element f here, you can consider a map from C infinity m to itself that takes function g to f times g. So now another important class is higher order differential operators. So this form a subspace. I will call it d less or equal than r. So this is a subspace here. So I will refer to the differential operators of order less or equal than r. So so what is this? So differential operators of order less or equal than 0 is just multiplication by functions. Now, differential operators of order r, less or equal than r, well, it's something that there are two ways to define. So if you have a coordinate chart, a differential operator of degree less or equal than r on Rn is something that it's an operator on functions that can be expressed as in terms of partial derivatives, right? So it's differential operator of degree r if the kind of total order of partial derivatives is less or equal than none. So you can take, for example, something like dx1, dx2, and multiplied by a function, and so take various sums of this. So the total order must be less or equal than none. This is a definition which kind of refers to coordinate charts. So you may ask whether it's possible to characterize differential operators algebraically, right? So, for example, we characterize vector fields as linear maps from C infinity M to itself that satisfies the Leibniz form. Is there kind of a version of kind of higher order of Leibniz form, right? So what is the algebraic property that operators of this type, even for Rn, have? So is it any ideas? What would be, how could you give a coordinate-free definition of this?
Well, as far as I know, there is some formula such that for example, fg, and if we take the derivative, for example, r times, then we have f to the power of r times g plus r times f to the power of r minus 1 times g, and with these Newton binomial coefficients.
Okay, so let me try to write it down. So so suppose I have d in this d less or equal than r. So so what is it? So you suggest to write something of this type, right? But right. So indeed, if there is a generalization of the Leibniz formula for iterated for higher order derivatives, right? So, for example, if you take rth iterated derivative, it's equal to binomial coefficients IR if I G R minus I. Is it the formula you were alluding to?
Yes, this is the one.
Okay. But it's not, however, that obvious how to make sense of this formula. So for me, sort of, I want to characterize those endomorphisms of the vector space of C infinity functions that can be expressed as combination of iterated derivatives. And well, so I'm just given D, right? It's just one endomorphism. There is no like derivative of smaller order. I don't know what to put here, right?
Yes.
So so here is the following. So what one can do is to kind of make an inductive definition. So so again, so d less or equal than 0 is just C infinity m, and you think of this as multiplication by functions. Okay, so multiplication by functions, it's these are very special operators from C infinity m to itself. They have the property that they commute this multiplication by functions, right? So this C infinity m is a ring. So and in particular, it's a module over C infinity m. So you can consider simply every operator from C infinity m to itself, which commutes with multiplication by a function, is itself multiplication by a function, obviously. You just look where 1 goes. So now I will define d less or equal than r of n is the set of all d here such that for any function, its commutator with d is a differential operator of order less or equal than r minus 1. So what is the idea behind this definition is that if you say consider d squared over second derivative, if you commute it with a function, take the commutator, right? You get also a differential operator, but of lower degree. So how does it work? So you you use Leibniz formula many times. So it's d over dx f product minus, this is not partial derivative, right? That's composition of 3 operators: multiplication by a function, derivative with respect to x, and another derivative. So if you compute this commutator, what is it going to be? So it's you do it. This is d over dx. Then you have f d over dx minus f prime. Right? You just apply the Leibniz formula. D over dx multiplied by x by f is equal to this difference. Sorry, plus. Remember that f prime stands for the operator of multiplication by this function, derivative of f with respect to x. So minus f dx composed with dx, and then you apply Leibniz formula once again. What you'll get is f prime d over dx and then you will have plus f prime d over dx plus f double prime. So this is 2f prime d over dx plus f double prime. So you see that you take a differential operator of order 2, you commute it with a function, and you get an operator of degree 1, which is just partial derivative multiplied by f prime plus multiplication by second derivative. In general, if you have an expression, combination of partial derivatives of order less or equal than r, and commute it as a function, you get something of order less or equal than r minus 1. That's kind of the idea behind this definition. It turns out that, for example, for r, every linear map, so this is an inductive definition. So d0 is just multiplication by a function. d1 is happens to be just a vector field plus multiplication by a function. d2 is any element of d less or equal than 2 is has the form f times second derivative plus g times first derivative plus some h. So that's what you get, what you expect. Okay, so inside this enormous algebra, you have an important subalgebra of differential operators. These are kind of operators which are local in the sense that if you have a differential operator, you want to apply it to a function computed at some point x, then the result depends only on a small behavior of your function f in the small neighborhood of x. Okay, so let me so what else do I want to say about vector field? So so let me that was a side remark, and another remark. So I want to suppose I want to describe the kind of compute. Let me give an example. Suppose I have my manifold M is the zero locus is a subset of another manifold N, and suppose that it's given as a zero set of a function. So set of all points in N with the property that f of x is equal to 0. So I have a manifold N, and I have a function, C infinity function now. So think, for example, of N being Rn, and f is a quadratic form, or just maybe sum of squares minus 1, so something given by equation. So let's assume that for every point of M, derivative of f. So f is a map from M to R, right? And we have a notion of derivative or differential, that's another name for the same object, is not equal to 0. This is a map from T xm to R, right? In coordinates it's given by partial derivatives of f. Suppose that it's not equal to 0. So one of the partial derivatives is not equal to 0 for every point of x, for every point of f. Then, as we discussed last time, M has a smooth structure. Smooth structure. Well, it's characterized by the property that functions on M, smooth functions, are those continuous functions that are restriction of smooth functions on M. Right? Now, what is the tangent space? Suppose I have a point x in N. So I want to compare the tangent space to N and the tangent space to M. So by very definition, this space is the space of all derivations. And so this formula makes it obvious that you have a surjective map, the restriction map. Every function on M is a restriction of a smooth function on M. So if I have a derivation here, I can compose it with this restriction map and get a derivation of smooth functions on M. So this gives me an embedding of vector spaces, right? Now, I want to characterize the image. So what are those derivations of N that are factored through the restriction map? That can be factored through the restriction map. Factored through the restriction map. So, well, there is an obvious necessary condition. If you have a function on N, so suppose I give myself a derivation, d. When does it factor through C infinity M? Well, there is an obvious necessary condition. So if you have a function whose restriction to M is 0, then d of this function must be 0. So in particular, so if say d belongs to this subspace, then g of f must be 0. Right? But I claim that this condition is also sufficient. That the subspace can be characterized. In fact, it has codimension 1, and it's characterized by this unique condition that derivations tangent vectors to M are those tangent vectors to N that have this property. Well, why?
Excuse me?
Yes?
F is the same F as we have above, or is another one?
Yes. Yeah, F is the same as we have. F is the function that defines, that cuts this, cuts off this submanifold M. Mm-hmm.
Okay.
Yeah, thank you. So this condition again is necessary because restriction of f is a function on n, and restriction of this function to m is 0. So if you go this way, you definitely get 0. So you should, this composition must be also 0. So why this condition is sufficient? Just because by implicit function theorem, this M is a smooth manifold of codimension 1. So if N is n-dimensional, then M is n-1 dimensional. So that means that this is a subspace of codimension 1. And this is a non-trivial condition. So if F is if f is any function satisfying this property, then there exists at least one derivation for which d of f is not equal to 0, right? Why this is true? Because what we proved last time, not only that M has a smooth structure, we proved that locally N, together this pair M, N, is diffeomorphic to Rn. You can construct for every point x in M, you can construct an open chart for M containing this point. So a diffeomorphism of an open neighborhood with Rn that maps M to Rn minus 1. And then it's clear that so locally this this M is given by one equation, just the first coordinate is equal to 0. And then it's clear that if you take for g, then it's clear that the tangent space has that this condition, right, that the partial derivative with respect to this first coordinate is the condition is that derivative of the first coordinate is 0, cuts off of subspace of codimension 1. So this is a non-trivial condition. So that means that this has codimension, this space has dimension n-1, and this space also has dimension n-1. Therefore, this embedding is actually nice. This condition is sufficient. Okay, so this is a way to compute the tangent space of a manifold given by equations. Let me give an example. So let's take S2 sitting inside R3. So I take for my function f, of course, x squared plus y squared z squared minus 1. So we can describe the tangent space to S2, and we actually can describe the tangent bundle to S2. So so what is the tangent bundle? So the tangent bundle consists of a vector A in S2, right? And I think of this as sitting in R3, it's a vector, plus another vector, R3, right? So, so what is the point of the tangent bundle? It's a point of S2 plus a point of the corresponding tangent space. And the tangent space, we think of this tangent space as sitting inside this tangent space, which is R3, right? And this tangent space is given by one equation that, well, we look at those derivations that annihilate this function, right? So this condition can be expressed as saying that the dot product of A and B of these two vectors is equal to 0, right? So indeed, just write B in as B0 d over dx plus B1 d over dy plus B2 d over dz. And so the condition is that if you take this, differentiate f with respect to b, you get 0. That's equivalent to saying that this dot product is 0. Okay?
And generally, there should be a gradient of f instead of a. Is it true?
Yes. Yes.
And because we have a sphere, then a and gradient are collinear, and we can write it this way. But if we had an ellipsoid, it wouldn't be true. We would have to write something else.
Yes. So this condition is saying that the gradient is 0 is well, it's equivalent to this condition. Very good. So so we realized this tangent bundle as a subspace of S2 times R3 satisfying, which consists of all pairs satisfying this condition. Very good. So it's just, again, this TS2 is given as a 0 locus of a function on S2 times R3. And this function is the dot product. This function. It's this function is has the similar property. Its derivative never vanishes on T2 of S2. So this gives T of S2 a structure of a sort of a submanifold here. It's again, it's a closed subset here, and smooth functions here are those that are restrictions of smooth functions. Okay, so now, so what is this kind of defines the tangent bundle to S2 by equations, but it doesn't kind of quite explain what T of S2 really is. How it's how does it look like? For example, can you use this to prove that this tangent bundle is not trivial? So say, is it true that is it true that T of S2 is diffeomorphic to S2 times R2 or not? Well, so let's try to understand the sort of the topological structure of this space. So, well, so what can we use here? So so first of all, if you we have a map from this tangent bundle to positive real numbers. Well, so if you think of T of S2 of the tangent bundle as pairs A, comma B, where A is a point in S2 and B is the tangent vector, which is a vector in R3 orthogonal to A, then this map simply takes it to this pair to the norm of B, right? Norm of B, which is square root of sum of squares. So you have a sphere, and so you have a tangent vector. Now we identified, right? This formula identifies the tangent space to a point A with just with the orthogonal to this vector. That's what we should have expected, right? So if you have a vector in this this plane, which we think as a vector in R3, you just take its norm. So so we can consider subspace here, which is simply let's say T1 TS2 1 and by definition this consists of all pairs A, comma B in TS2 with norm of B equal to 1. And it's immediate from this picture that TS2 decomposes as TS2 1 times R greater than 0. So namely, so if you have a point in the sphere and a tangent vector, you can first rescale your tangent vector to make it have length 1. And so this will be a point here. And this is just the norm of this vector. Okay. Now, so we reduce to kind of understanding the structure of this manifold, which is better because now it has, so this was 4-dimensional, so this is 3-dimensional. So let's try, so to prove the claim here is that T S2 1, first of all, as a set, it's in bijection with elements of the special orthogonal group S3R. And this group, elements of this group itself, are in bijection with points of the real projective space, RP3, right? So let me understand this. Let me prove this. So what you do? So how to? Okay. So first of all, this group acts on the sphere, right? so S for 3R, it acts on CS2. Well, this is especially obvious if you think of points here as pairs, A, comma B, such that the dot product is 0, right? So norm of A is 1, right? It's on the sphere. SO3 acts on three-dimensional space on R3, and it preserves the dot product. Particularly, it preserves the norm. So you just take a pair A, comma B and send it and apply your matrix both to A and B and get another pair satisfying this property. So I claim that the action of SO3 on CS21 is simple and transitive. What does it mean? It means that if you have 2 points, if you have 2 pairs, right? So S21 consists of all pairs A, comma B. These are 2 vectors in R3 with the property that norm of A equal to norm of B equal to 1, and also the dot product is 0, right? So okay, so why this is so we want to show that the stabilizer of every point is trivial, and any 2 points can be transformed one to the other by an element of S or 3R. Okay, so first of all, using...
Excuse me?
Yes?
Simple means that stabilizer of each point is trivial.
Trivial, yes. Okay, so first of all, using an orthogonal transformation, you can move any point on the sphere to, say, the North Pole, right? It's enough to assume that it's enough to prove the assertion for, well, it's enough to prove the following, that if you have 2 tangent vectors of norm 1 at the North Pole of your sphere, then one tangent vector can be transformed to another by a unique element of S or 3R that preserve this North Pole, but that preserve this North Pole. But okay, so any transformation, any orthogonal matrix, special orthogonal matrix, which takes this North Pole to itself, is a rotation along z-axis, right? So there exists a unique rotation that takes this vector to this vector. Is it clear? So I think that the fact that the action is simple and transitive is geometrically, it's immediate. So now just choose any point on any point here on CS21, then so the stabilizer of the orbit of this point, which is S or 3R, is the whole space. So this identifies this action, this fact that the action is simple and transitive, identifies S to 1 with S or 3R. Mm-hmm. So this was
excuse me.
yes.
How do we establish this correspondence? So it's for each point of TS2 we.
So I choose one point here. Fix one point here. For example, take the North Pole and any tangent vector of norm 1. Fix it. So you pick a point here. Let's call it P. And then you define a map that takes G to G of P. Okay. If you have any set on which a group acts simply and transitively, then choice of a point in this set identifies the set with the group. Okay, because it's one orbit, and this orbit is sort of nature of bijection with elements of the group. Very good. So we have a bijection between sets. That was one claim, but so I claim that it's not only a bijection. It's actually a diffeomorphism. Well, to make sense of this, one has to realize this group as a smooth manifold. But what is this group? This is a group of all matrices satisfying the property that A times A transpose is 1. So this is a subset of the affine space of the vector space of all 3 times 3 matrices cut by this equation. So in order to show that SO3R is to give a structure of a manifold on S3R, it suffices to check that this equation is so this equation gives you can think of this as a zero locus of a map from 3 times 3 matrices to itself. So it's actually well, it's enough to show that well, the subset given by this equation is a submanifold. So so A times A transpose, you have all matrices, 3 times 3 matrices. It's a 9-dimensional vector space. And so this formula A times A transpose gives a map to symmetric matrices. Symmetric matrices, which is also a vector space. It has dimension, it's R6. So so SO3 is a preimage of one point of this map. It's given by this formula. A goes to A transpose times A times A transpose. So one has to verify that the derivative of this map is surjective. Then the general theorem from the last time implies that the level set of this map, so where the preimage of 1 is a submanifold. So so with you can also define smooth structure here explicitly. So a smooth function on SO3R is just a smooth function in coordinates of your matrix, in the entries of your matrix. so and it's at least believable that the map, the bijection that we defined, is actually diffeomorphism. Okay. So my time is over. So let me stop here. I still have to explain why this group SO3R is diffeomorphic to Rp3. This is a beautiful piece of linear algebra. So let's come back to this next time. So, but I want to sort of give you, I want to offer you another exercise. So using this fact that assuming that this tangent bundle is diffeomorphic to Rp3, show that the tangent bundle exercise using that T S2 1 is Rp3, show that there are no non-vanishing vector fields. Honestly. Okay, so so the idea is that if you have a non-vanishing vector field, this makes the tangent bundle to S2 trivial, and gain by removing the zero section from your tangent bundle. So in particular, it would mean that if you remove the zero section from your tangent bundle, it becomes diffeomorphic to S2 times R2 minus 0. And on the other hand, this diffeomorphism shows that that's impossible. So you need to use a little bit of algebraic topology, namely the information, well, the fact that the notion of fundamental group, that the fundamental group of the real projective space is Z mod to Z. Okay, so I would like to stop here. So this lecture has been recorded, and it will be, the recording will be, the video will be downloaded to the department webpage. Thank you very much. Any questions? Well, if not, let's stop here. See you next time.
Thank you very much.